All right, welcome everybody to the Scour session this morning. My name is David Spinks. I'm the moderator. I'm from Tennessee DOT. We've got a pretty good slate of presentations today. I guess since we're a little bit late starting, we'll go ahead and get right into it. Our first speaker is Dr. Hubert Ley. Dr. Ley started at Argonne National Laboratory in 1991 as a nuclear engineer and has worked on the development and deployment of a wide variety of simulation codes. He became the director of Argonne's Transportation Research and Analysis Computing Center in 2010 and manages now a diverse group of scientists with expertise in computational fluid dynamics, computational structural mechanics, nuclear plant diagnostics, and optimization, and machine learning application. He also operates the TRAC High Performance Computing User Facility for US DOT, providing massive computing resources to various US DOT programs. With his experience in programming and simulation, he has led the development of the OpenFOAM Pure Scour code development for the past 3 years. He worked on this with Dr. Stephen Lotz, who was unfortunately unable to attend. But anyway, welcome Dr. Ley.
Very good, thanks. All right, the microphone works already. Can you hear me? All right, very good. Let me find, oh, it's a Mac. How do I find my presentation? Does anybody know anything about Macs?
So look on the far right next to the trash can.
Yep.
One of those would be the right one.
And that would, no, that was not it. It blinked up for a moment. I can't believe I'm supposedly know something about computers. But Macintoshes just leave me stymied because I never use them. Yep, there we go. There. Very good. All right. Oh, and it didn't start at the front. So I just back page a little bit. Takes a moment. I can start talking. So while I do all these things at Argonne and have a career and all kinds of things behind me, I really like the practical work. So here I got really into the whole programming with OpenFOAM and Python and things like that to help with the Scour development that we are doing here. So we're working very closely with Cornell Carenier and the hydraulics lab at Turner Fairbank. And we have all kinds of things in mind for the future. Right now, this is research, right? So very strictly, we're trying to work with the hydraulics laboratory on making sure that any CFD calculations correspond to experiments, so the comparative experiments that are being run and so on. But one of the things that we already do is upscaling things from the flume to the field scale, because that is much easier to do in a computer, because obviously you cannot run field scale experiments. Right? So in the short term, we're developing all these things, but in the longer term, what we have in mind is to move towards developing a tool that can be used by others, which is one of the reasons that we do this in an open source environment where it's easy to distribute the software at no additional cost to people. Right? So you also see in the midterm goals here, right? We would like to combine the 3D CFD Scour software with 2D runs, like SRH2D, for example. It's because a 2D run can cover a much larger area. You'll see that in one of the slides later on as well, right? So ultimately, what we are trying to accomplish is really get a design tool out that can be distributed to practitioners. And it will probably take quite a few years for us to learn exactly what you need, because people like us in the ivory tower, we are somewhat disconnected from the practical use of these kinds of applications, right? So there will be more and more collaboration with interested parties. Cornell will make sure that we keep everybody in the loop who needs to be in the loop to make this an effective transition. So one of the problems with Scour is that physically, the processes that started, they happen very fast based on flow patterns, right? But then the erosion itself takes a long time. And the later you get in your case, the bigger the time steps. So things change slower later on, right? So if you just run a CFD case and you want to model the riverbed within that CFD case, then you very easily run into computation times of, let's say, 10 years or something like that, right? I mean, if you estimate how long it would take to run something purely as a CFD case and not use some kind of a trick to accelerate the process, right? So we came up with an idea over the years where we separate the flow calculation from the erosion calculation, so they both run on a different time scale, and that way we can pack that easily into a runtime of, let's say, a day, at the most a week or something like that, on a really powerful computer. I mean, a single computer that somebody could easily operate. Right now we have a big cluster computer, we can use many of them. So, but the goal is to have this down so that it runs on an application computer for one of you. This is easier to explain in concept when you look at pictures, right? So we can deal with very, very complex bridge structures, right? So you see here the Pier 22 from the Feather River Bridge that is redesigned and has an extremely complex shape. Lots of H-piles in the center, the cylindrical piles around, right? So what we do is we embed that into a three-dimensional model, right? That's just the long bar at the top. And of course, I'm not showing the water level, right? I mean, this is just the river bottom, but this is a three-dimensional calculation of all the patterns on how the water develops eddies and runs around the pier. So what we're really looking at, and that's what you see on the upper right, are the bed shear stresses. We have to accommodate for going downhill and uphill in the direction of the shear stress vector, but that gives us a very good pickup function for the sand. So it's based on the Van Ryn formulation for sand, so you have a certain grain size, typically 1 millimeter, all the way down to 0.2. We also do it with clay in a very, very experimental stage, right? And then we have three things that happen. The Van Ryn formulation tells us how much sand gets picked up because of the shear stress. Sorry, the shear stress, right? And then once the material gets into the flow in the CFD calculation, it moves along as a dispersed phase within the flow field. So it's a multi-phase calculation where you can have discrete particles represented as a fraction of volume in the cells, right? And then once the material experiences flow conditions where it starts to build up, we know that that is where it has to deposit it. That's the most difficult piece to explain because we have to go deep into theory with divergence and things like that, right? But we have a way to tell where the material falls out onto the bed again, right? And it never falls out nicely, right? It will always have steep piles or sharp holes. So we have also a sandslide algorithm that goes over the whole thing after each step, right? And the sandslide makes sure that we have a nice, smooth slide into the hole. So here you see the final riverbed after you apply these few steps, right? And this is the riverbed on which we apply the thing in blue and triangles, right? And then we use the measure from the CFD software to build a CFD domain based on the shape of that and the bridge structure and everything. And we are ready for the next CFD run. And we do that a few hundred times. So here is a diagram that's already a little bit too detailed, unfortunately, but it's based on what I explained before. So here is a little screenshot of my previous slide, right? And each of the progression from one dot to the next red dot means that we're progressing through one of those outer cycles. So on the left, you see about 15 of them, right? And the blue line is a mass balance that we calculate in the CFD solver. And when our mass balances drop down, eventually to 1% or something like that, then we know that we have a consistent numerical solution, and we can use the shear stresses to calculate the erosion rates. And then on this graph here, you see the scour depth increasing, right? So you have the scour depth on the y-axis and the time here. Now the CFD runs for, let's say, 5 to 10 seconds of simulation time, right? That is on a computer maybe a half hour, an hour, something like that. And then the scale for the erosion is, of course, now totally separate from that, right? Because we can apply the erosion for a long time frame until the shape of the riverbed changes more than a typical cell size, right? So then we would move forward. Let me grab this piece before I break the property here. So there we go, all good. So then we have the same thing in lots of words if you ever get your hands on these slides. So I'm skipping over this, right? It's easier to explain the thing with the graphics. So there's another thing, right? We have access to very expensive software. So the Siemens Star CCM Plus software that we use for most of our work, that costs us in the neighborhood of $100,000 in licensing fees a year, just to have a few users work with it, right? And so using something like this is not practical if we ever want to give access to the software to anybody else, right? So 3 years ago, we started developing this stuff in OpenFOAM, which is a freely available piece of software, right? Readily installs on pretty much any computer. It's a little harder to work with, but has very similar capabilities, right? So I'm giving you an example here where we compared those two pieces of software with each other. So this is the flume that Cornell has in Washington at Turner Fairbank in his hydraulics lab, right? That's the picture on the upper right. And then you have a flow straightener in there with all the little pipes. I don't know whether the resolution is good enough to see that. And then under the blue lid, you have that center standpipe with 400 holes in it, right, where the water comes through the bottom and then gets into the tank. And you get as straight of a flow as possible in that arrangement. And we were analyzing that for a project for the Army Corps of Engineers. And so on the left, on the bottom, you see the results that come out of the commercial software, Star CCM Plus, right? And then the same case, well, same geometry, but everything else was set up separately, right? Runs then OpenFOAM on the right. So you see the streamlines, the velocities, the water levels in the flume, things like that, right? So this is very typical for what we're doing. We never, ever trust the code, right? I mean, the computer can make, I don't know how many billions of mistakes per second, right? I mean, you really have to keep that in mind. And so when you're a modeler like this, right, you never trust your result. The trick is to use another piece of software, and then you can start throwing out reality. Now, the experiments are still better, right? And you'll see how we eventually get there. But while this is an extremely fine-grained model that we do, right, it is still a very rough tool when you think about it, right? I mean, reality is so incredibly complex that even with the most computers, you cannot really get there all the way. So, a few nice little videos to get you an idea, right? So this is the whole thing in action with a spill-through abutment. And what you see is that we have the shear stresses, and the riverbed now moves down, right? So here you have the spill-through abutment. You have even the sand. I don't know, the contrast is probably pretty poor, but here you already see how the sand from under the bridge deck in the street starts slipping down into the hole, right? We also run this then with all kinds of variations, and you see it for wing walls and field size and so on, right, with different gaps and things like that. And Cornell is going to set up those kinds of experiments in the flume pretty soon, because now he has the right size flume in place. But what you don't have here at all is the deposition of sediment, right? And what you get as a result is a scour hole that's probably very unrealistic, right? Because the stuff that gets picked up is dissolved like salt into the water, right? For a first shot, that was good enough, right? And it really shows how you can do this easily and expose, for example, all the piles under the pile caps. I mean, you can throw very, very complex bridge geometries at the problem. Here's another example. The large area that you see, so the green, blue, whitish kind of stuff, that's an SRH2D model, right? And we took a particular smaller part out of this, and we're interested in this bridge, but we wanted to see how big of a model can we build, right? And so this one was really running in very reasonable time. And here what we did is we have a riverbed where we have sand, and the sand gets all eroded away, and then you end up with a clay layer under there that's exposed, right? And at the clay layer, we would then, of course, use now different erosion parameters. In the long term, the tool can easily accommodate multiple layers of material, and the the properties of the materials change as the scour hole develops. Right now, we do it with one material, but the theory is easy to extend to multiple layers, right? So that's not a big of a problem. Here's another case like that. This is the same bridge that you saw yesterday in James and Cornell's presentation, the bridge over the Saginaw River in Lafayette Avenue Bridge over the Saginaw River, right? And so the problem that they described yesterday, or let's say the lucky solution, is that there is a clay layer in the under the sand layer that you have on top, right? And for the purpose of demonstrating how our software works, we ran sand erosion here on the lower left until the clay got exposed, right? So you have now these clay patches close to the piers where the scour holes for the sand develop. But we wanted to see how does the whole riverbed conservatively behave if this is all clay erosion, right? So let me see whether I can easily restart the video. I think, is it playing? It's a Mac, everything is deformed. Yeah, I think something is moving. Yeah, okay, so that's fine. So what you see here on the top now is a totally different thing. We start with the final stage that we see here, and then we assume that the riverbed shape with the clay and with the sand is now all clay, right? And that is something that we then can run through a clay erosion simulation, right? And what you easily see is not so much is happening, right? I mean, you have that one dip here by about 4 feet. I put a grid in there so you see this a little better, right? So the brown line, that is where the clay layer is. And then the orange and the pink line, those are the current methods estimation for Q100 and Q500, right? So to make things really dramatic, we chose a Q500 case and increased the flow by 35% because otherwise you don't see any erosion on the clay at all, right? And then it took us a flood of 75 years at those idiotic conditions to actually go down by 4 feet, right? So that was kind of the proof that the clay basically stops the erosion under these foundations, right? Moving on, now the sediment transport. So you have seen 4 years ago, if you were here, the plot on the top left, right? So this was our scour hole, and that was done with the StarCCM Plus software, with the commercial software. And on the bottom right, you see the shape of the final scour hole at the very end when you have the case with the cylindrical pier, right? And the one on the top left that we had 4 years ago didn't have the sediment transport in it yet. So 2 years ago, Steve came to something like you see on the top right, and that is an inclusion of sediment transport, right? And he ran this case to the very end, and what you see is more of a development of large dunes. You can see that in some of the other videos later. That is a discretization problem, right? Because much of the sand moves in form of dunes, which means lots and lots of little changes to the riverbed in areas that are not terribly interesting, right? And so our newest thing that we started with OpenFOAM, and I didn't run this very long yet, so the shape of the deposition is not final by any means, right? But what you see here is that when we dig to maybe 60 millimeters, the other one go to 125, 130, something like that. So this is not the final stage. Maybe this is 25% into the case or so, right? We see these lobes forming here where the material deposits, right? So it took small time steps in the erosion scale, but this only ran for a few days, like a couple days or something like that. And then we had an experiment that Cornell did for us that took a video camera underwater to show how the erosion patterns look like, right? And I don't want to overpromise, right? But what I get out of this kind of calculation looks somewhat similar, right? That's very promising, at least in the early stages, right? So it shows that the physical phenomena are probably correctly caught at this point, but it's completely uncalibrated, right? So I'm running this without tweaking any numbers. It's the exact Van Ryn formulation and so on. Because when you develop this kind of thing, you don't want to put any kind of smudge factors in there. I rather explain why things look different. Right? So here we go now and really throw some complexity at the problem, right? So we have this Pier 22 with the extremely complicated geometry, and we have the picture from the flume with the final shape of the scour hole, and here you can see now how that develops. So on the top right, you see how a single one of those piers behaves. But because it's just an STL file, the same thing you would send to a 3D printer, right? So it's very easy to generate them out of CAD software and things like that. You can build any complicated geometry, so I just packed 3 of those piers into a single STL file and run the software, same thing with 2, right? And you see that when you have multiple piers, there is a lot of interaction with regards to the scour hole depth, right? Now here the flow comes exactly at 45 degrees. 45 degrees means that you have a lot of flow redirection once you have multiple piers, right? So the flow comes from here, but because these piers act like veins, you also direct the flow around. So the material that gets dug up here piles up here, but then this angle, the slope here, is always the angle of repose because of that sandslide algorithm. So material gets transported out of the hole, builds a hill, slips down into the next scour hole, right, and then gets picked up again and moves out to the position behind the next pier, right? So this kind of stuff can all be caught with the software, right? And so when you compare it now to the shape of the scour on the top left, right? We're not exactly at full depth yet with the simulation. It was still running last week when I made the slides, and I haven't looked at it because I'm here at the conference, right? But this is very promising the way it develops, right? And the experiment was done under the exact same conditions. You see a slight difference with regards to the formation of the scour holes. I mean, there are features on the hills that we're obviously not capturing perfectly or so. But then again, we only care what happens in the scour hole, right? I mean, building up a little hill behind the bridge pier is not the most important thing. But I was surprised myself how well this actually works. We have one more. And this is an arrangement in the flume that Cornell ran in the lab, right? So here you have a 6-foot flume, and you have these 2 blocks. I think the opening between the blocks is about 18 inches, right? So it's less than a third of the overall flume width. So what you get is a very high acceleration of the flow into this, right? You also get a whole bunch of eddies and things like that. And maybe this is one of the slides where we can explain also some of the things that we have to look into the future, right? So compared to what you see in the experiment at the end and what you see in our run, about 75% into this thing, so that we have reached 140 millimeters. I think the final depth of that hole in the experiment was 200. Right? So there's still a way to go, but what you see is that we're not piling up enough material behind the piers. We're capturing the development of the scour holes really nicely. We are capturing the slope up onto the deposit area pretty well, but then the material gets moved out of the domain and doesn't pile up correctly. This is partially a calibration issue, right? Because we have to develop some theory here. One of the things that helps with the deposition is that we have a friction model of the dispersed sand with a riverbed, and we have no idea what to properly set, right? We also have a layer of sand floating over the riverbed, and this might be actually interesting. We're not talking about multiple cells worth of sand within our simulation. We're talking about small fractions within the first layer. Right? The most material you can pack in the first layer is 60% anyway. Right? That's the packing density of sand and water at this 1 millimeter diameter. So we are transporting a layer of sand, but it's probably quite a few grains thick, right? And so at that point, how do you properly describe friction and things like that, right? Now, mostly this is important for two things. One, the far away formation where the water flow slows down on the riverbed, right? That's where mountains would form. The other thing where we have to get it right, and that's why we still have to look into this, right in the center of our bridge opening, there might be material deposited, right? I mean, let me try to go back. I think this is my last slide anyway, so let me start it over again. So you see that the material is piled up initially between the piers. So everything yellow is above original ground, right? What we would expect now is that the material behind the piers spreads out a little more. Now here's another simplification that we had to make to save compute time. This is a K epsilon model, right? So turbulence is modeled in form of more energy, basically thicker water when you think about it, right? And so with this kind of model, you don't catch all the eddies that shed off at the corners after the opening and things like that, right? And so the stream goes straight through the rest of the water, and we have to find out whether we have to use large eddy simulations, or maybe it's not important, maybe it's just a scaling issue, right? So you see how this is not exactly ready for prime time yet. But you also see, when you compare experiments and our initial runs, and most of them have been done in the last few weeks, the similarity is pretty significant, right? So I would not build a bridge based on this, right? But if we verify this kind of thing in the flume, and then scale it up in the software to the field size structures, because that is something that CFD software can do a whole lot better, because you simply cannot run it at the large size, right? Then we should be in pretty good shape to get a good design tool out of this. So that's pretty much the end of my presentation. So if anybody has any questions, suggestions, yeah, go ahead.
Thank you very much. That's very enjoyable. I was just wondering if you've trialed other turbulence models, i.e. the OpenFOAM, SST.
I haven't, right? And so I'm also the wrong person to ask. I have been working on this for only 3 years, right? So my specialty is really the software development, getting the numerical methods all implemented and things like that. Steve Lodis is our theoretical expert, right? And I have worked very closely with him, and he has provided all the details. I cannot tell you why we have not used different models. They're certainly available. I mean, K omega is definitely available in OpenFOAM, right? So that would be certainly something to look into. Any idea? Oh, Martha has an answer. Excellent. Go on.
So those few years ago when we were working still with Starsian Plus, I remember that we tried different.
You did. Okay.
And it just didn't change much back then. But right now with your new script,
It might. We should try. I mean, it should be easy enough to swap one model out for the other one, right? And this puts the finger on a lot of these things, right? I mean, there are so many parameters that you can change, right? So we try to minimize that so that we see from every evolutionary step of the software to the next whether things get messed up. If you make too many changes at a time, that becomes difficult, right? But yeah. And then just for curiosity, I mean, whoever has experience with SIH 2D and things like that, right? You can imagine that if you have a two-dimensional flow solution, that you could embed something like this in the middle of the 2D domain, right? And then you take in the flow field from the 2D domain. Okay, you have to make it three-dimensional. Then you use a seventh power law or something like that to get your velocity profile right. But you could then do the detailed calculations based on better input conditions, right? Because we can only capture certain domain sizes. You saw that, right? I mean, we are several bridge lengths away or something like that. Maybe we can drive that distance a little more. But it would be better to see, especially for flood calculations, to get better input from a larger scale model, right? I have done this. I have just for fun, right? I mean, once you know that the input are just STL files, right? To put some tree trunks in there. I haven't tried cows yet, but the funny thing is I have tried a car, right? I mean, I just needed geometry, so I just downloaded some STL files for 3D printing and stuck them into the model. And it's easy, because, I mean, the STL file of the bridge structure, let me go back to this one here, right? So the one on the top left, you just load it in your CAD software, and you load it in 3 different locations. You save it as a single STL file, you go, right? So the easiest thing with debris would be to just make it part of the bridge structure file, right? At some point, I even put some riprap in there, right? The riprap cannot move. I mean, that's one of the problems, right? So when you put things in as a bridge structure, it's static throughout the whole thing. But you see interesting effects when you clog up these openings with debris, that's for sure. All right. Oh, I'm well over, so.
Well, we got a little bit of a pause
Okay,
for you.
very good.
That's about it.
Okay, thank you very much.
Thank you very much.